So, starting you off with a problem on the board today that actually is one that I would argue you probably already know how to do, but I'm going to try and tie it into what we've done and what we're doing. Okay? So in this particular problem, it says, how many ways can you arrange 4 paintings on a wall? Alright? So for this particular problem, we're going to assume that you have enough room on your wall for all 4 of these paintings, and all 4 of them are different. Okay? So we would like to know, in how many different ways can you arrange all those paintings? Okay? Now again, it's the same 4 paintings no matter what. But if I were to take painting 1 and painting 2 and I flip-flop their location, okay, that's going to be a different arrangement along the way. Okay? So one way to be able to do this problem would be to do the long method of doing the tree diagram. Okay? And so you could sit here and say, well, if I put picture number 1 in the very first spot, what are all the different ways that I could do that? So one thing that I could look at and say is, well, what if I just put them in order and said I have 1, 2, 3, and 4? Okay? But then, like I said, you really got to get picky with all these different arrangements, because if I did 1, 2, 4, and 3, that would be a different arrangement. Okay? So I would need to think of all the different ways that I could move these paintings around and then not be something that I've already counted. Okay? And so, again, you can see here I just flipped these 2, but I might take this and I might just flip the middle 2. Or I might take this and I might flip the first or the second and the last. That's also something that is different. Okay? And so, again, rather than drawing a picture, if I just numbered them as 1, 2, 3, 4, this is a little bit faster way for me to figure out all the different arrangements. But unfortunately, it's still going to be really time consuming. Okay? So, really one way to be able to do this problem, and it ties in very nicely with what we've already done, is if you'd like to know the number of different ways that something can happen, it boils down to the multiplication principle. Okay? If I'm choosing from the first picture to put a picture into the first spot, I'd ask myself, how many choices do I have? How many for the second spot? How many for the third spot? How many for the fourth spot? Okay? So tying it into what we did last week in the assessment that you took, this is how I would tell you to kind of think about this particular problem. Each one of those represents the 4 different spots that you can put a painting. So if I've got 4 of them and none of them are on the wall yet, how many choices do I have for that very first painting that I put up there? I got a total of 4 of them. Okay? And it doesn't matter if I put it in the first spot, second spot, third spot, or fourth spot. Ultimately, I have 4 choices for the first painting that I'm going to put up. Okay? After the first 4, or after I put the first one up, how many choices do I have for the second one? Now I only have 3. Okay? After I put the first 2 up, then for my third painting I've got 2. And then I get to the last spot, and how many choices do I have? I just have a total of 1. So if I want to know how many different arrangements this can have or happen with, I'm going to take the number of choices I have for each of those spots and simply multiply them all together. And so I can take 4 times 3 times 2 times 1, and this is going to end up giving me an answer of 24. I would have a total of 24 different arrangements that I could make out of these 4 photos. Does that make sense to everybody? Now, what if I added a 5th spot with a 5th photo? Well, if I change this 4 to a 5, and I added a 5th spot here, what's the only difference? Then I'd add more arrangements, because how many pictures would I have for my first spot? I would have 5 choices. But after that, I would still have 4, then 3, then 2, then 1, correct? Just like before. And so if I added a 5th photo to this, it doesn't take very long, and all of a sudden I'm up to 120. And then if I added a 6th photo, obviously I'd add a 6th spot with 6 options for my very first one. Okay? But what I want to show you is some of what we're going to do today, not all of it, some of what we're going to do today can be traced back to, this is the multiplication principle. And remember what the multiplication principle told us in the last section. It said this helps you find the number of different ways that something can happen. Okay? Again, I want to go back to that because why? Because the number of different ways something can happen helps us find probability that something is going to happen. Okay? All right. So we're going to revisit this within our notes here in a couple of minutes, but I at least wanted to throw this up here as our beginning problem to start us off. Okay? So today we're going to take a look at something called 11.6. Is all about this idea of permutations, which is a vocabulary term that I stated at the beginning of this unit, and I told everyone, I don't expect you to know it yet. But today is the day that we need to start to know what permutations are, okay? And I'm also going to show you some features that you can use on your calculator to help you with these computations here. And again, that's why I want you to use the calculator that you're going to use every day, okay? Now, a couple quick little things, actually, as I bring up calculators. Number one, the first one I opened up today had a cracked screen on it. This is brand new last week. You're the only class that uses them. I don't understand how we're getting cracked screens on this. And number two, I'm starting to notice the same diagram art on these as on your desks, which makes you really, really easy to figure out who it is, especially for some of you when that same art shows up on your checkouts that you handed in. I wonder who that is. Stop writing on stuff that's not yours. Don't write on your desks. Don't write on this. Okay? Have a little bit of appreciation for it. I don't come into your bedroom and start writing all over your walls. Don't write all over these desks. Don't write all over these calculators. Don't write all over these textbooks. Unless you'd like to purchase them, okay, your textbook's about $130, that calculator's $30, I can start billing you for it if you actually want it to be yours. Does that make sense? I would think as freshmen in high school, you probably understand that, but obviously some of us didn't. All right. So, today, we're going to start talking about permutations. And we're going to begin with the definition that I want to tie right back into our opening problem. Okay? Our opening problem, we had 4 paintings placed on a wall, 4 different, or how many different arrangements. And ultimately what we said was we were taking 4 times 3 times 2 times 1. We started with the number of choices we had on the first spot, and then we just worked our way down and we multiplied all the way down to 1. Okay? This actually happens so often in math that we give this a name. That you multiply 4 times 3 times 2 times 1, or 5 times 4 times 3 times 2 times 1, or 10 times 9 times 8 times 7 times 6, all the way down, then you want to do all these multiplications. Okay? And that's our very first definition today. It's called a factorial. It's actually an operation that most people don't realize is an operation. Okay? So here's what we're going to say. For any positive integer n, that's our positive integer. Okay? The product of the integers from 1 to n is called n factorial. Any positive integer n, the product of the integers from 1 to n is called n factorial. put the notation at the end of this. It is n with an exclamation point behind it. So, taking 1 times 2 times 3 times 4, just flipping the order of this, this is the product of all the integers from 1 to 4. So this right here is the same as 4 factorial. That's what the definition is. You've seen exclamation points, you assumed that they were only used in English, but they're actually a mathematical symbol. When I want to do a multiplication problem of consecutive integers and find out what their product is, I don't want to have to type that into my calculator all of the time, because some of those numbers are going to be rather large. Remember at the very beginning of this, when I asked you how many different seating arrangements we could make in this class, and I put a problem out, or put a number up on the board which was super, super long? How did I figure that out? It was a factorial problem. And there is one button on your calculator that actually will do that entire multiplication for you. Okay? So I actually want to show that to you right now before we go into our next definitions. If you would like to find the factorial of a number, okay, I'm using this calculator. A lot of you have this one. If you don't, I'm going to have to look at yours individually. Sorry. Got my definition of the way here. Okay? You're going to begin by typing in the number that you would like to find the factorial of. And we just started today's problem with 4 factorial. We already know the answer to this is what? 4 times 3 times 2 times 1 is what? Was 24. Okay? Now, I don't argue that you could type that in really fast into your calculator, but it's going to be worth your while to know where this button is at. So, on this particular calculator, you want to go to the button that talks about probability, which is this one right here, PRB. And if you go to PRB, you'll see in the first part of your menu these 3 choices. We're going to use all 3 of these over the next 2 days. Okay? The one that you're concerned with right now is that third one. So if you press the over arrow until that has the line underneath of it, and then press equals or enter, it's going to bring that symbol in here for you. And if you hit enter again or equals again, there's your answer. 4 times 3 times 2 times 1 is 24. Again, this is going to be nice when I'm starting to deal with large numbers. Okay, what if I have 10 paintings on the wall? That's 10 times 9 times 8 times 7 all the way down, or 10 factorial. My calculator should be able to do that for me. Okay? So just one quick feature your calculator is going to have that we're going to expect you to be able to use is your factorial button. Okay? Now, our next one, real quick definition. What if I have 0 factorial? Okay? And most of the time people are like, well, if you've got 0 factorial, it should just be 0. Because you're not finding the product of anything. But here's the thing, it's actually a little counterintuitive. It's almost like taking something to the 0th power. When you take something to the 0th power, ladies and gentlemen, remind us, what was our answer? 1. It was 1. Anything raised to the 0th power is equal to 1. Okay, and we even showed a little bit about why. Alright? That's the same thing we're going to define here. 0 factorial, which is this, is simply defined as 1. And that's our quick, easy definition for that one. Alright? Our next definition we're going to come back to here in a couple of minutes. What I would like you to do is in example 1, this is real quick and easy. You've got 4 problems, or 3 problems, sorry, 2 of which we've actually already done because I chose poorly for our opener. I would like you to use your calculator and find those 3 answers though. This is going to tell me and give me an opportunity, if you don't know where your factorial button is, give me an opportunity to help you find it. might not find the factorial button on their calculator. Alright, so there's our three answers. 4 factorial should be 24. 0 factorial should turn out to be equal to 1 from our definition above. And if I've got 6 factorial, then we're going to have a total of 720. Okay? Alright, now let's take a look at how you could do these problems. And again, I'm going to try and show these to you both ways so you kind of understand how these come up. So in example 2a, it says you have 3 books that you would like to, 3 new books that you would like to read. And how many different orders can you read them? Okay? So, a couple different ways to do this. And again, mathematically, we're looking at the exact same idea. This is a problem, example 2a, that I could have given you last week and you should have gotten the same answer. Okay? And here's why. You have choice 1, choice 2, and choice 3, and using the multiplication principle, you should have been able to determine out the number of ways to be able to do this. So how many choices do you have for the first book that you're going to read? 3. How many for the second book? 2. And how many for the third book? 1. And so if I multiply those all together, that's going to tell me the number of choices. This is the same as taking 3 factorial, because that's our definition. The product of 1, 2, 3 is the same as 3 factorial. So whether you want to use the counting principle for multiplication or your factorial idea, either one of those would work. But how many different ways are you going to have to read those 3 books? Total of 6 different ways. Because 3 choices for the first one, 2 for the second, 1 for the third, is a total of 6 ways for that to happen. Okay? Now, in example 2b, it says at tomorrow's track meet, there are 8 athletes who are running the 100-meter dash. And how many ways can this race be completed? So when it comes to who can finish first, how many different ways are there? 8, then 5, then 4, then 3, then 2, then 1, then 0. So if I want to view this as a multiplication problem, I've got 8 blanks for the 8 people that can finish there. And as you just pointed out, there are 8 choices for the first, 7, 6, 5, 4, 3, 2, and then 1. I can multiply those all together. Or, the product of this is the same as taking 8 factorial. And if we take 8 factorial, then we end up with what?
48,300.
That is the number of ways that that race can be finished with 8 different runners. All right, questions on that? Serena. I would take what you're going to show for your work. So if you just want to do 8 factorial, then that's going to be completely fine. Okay. Now, before I start tying it into this next idea, I want to consider the same problem. Okay? So, at tomorrow's track meet, 8 athletes running in the 100-meter dash. How many ways can the race be completed? Okay? So I was gone on Friday because I went to the Drake Relays, which is the biggest track meet in the state of Iowa. Okay? So I watched track all day Friday and Saturday. Really, let's face it, after the 3rd place finisher, it doesn't really matter, because the top 3 people are the ones that kind of get all their medals. Okay? So here'd be my question. If I have that same exact problem, okay, I don't care who finishes 4th through 8th. I just care who finishes 1st, 2nd, or 3rd. How many different ways can the top 3 people finish in that race? Is it going to be more or less than 40,320? It's going to be less. Because I don't care about 4th place, 5th place, 6th place, 7th place, or 8th place. I only care about 1st, 2nd, or 3rd. Okay? Does anybody think they know the answer? In how many different ways could those 8 racers finish 1st, 2nd, or 3rd? So you know, what's your thoughts? 13,440. Let me see. No. Cynthia, what do you think? 720. No. Caitlin? 336. Yes. Now, how did she get 336? Okay? Here's what I'm going to point out. Instead of having 8 blanks, we would only have 3 blanks. Because we're only worried about 1st, 2nd, and 3rd, right? How many choices would we have for 1st place? 8. How many for 2nd? 7. How many for 3rd? 6. And what are we going to do? We're going to multiply those together, still using our multiplication principle. And if I take 8 times 7 times 6, this is going to give me 336 possibilities. Now again, when I first started teaching this, that's the way that I viewed it. Alright? So, when I first started teaching this, I was taking grad class and I took a probability class. And this was a large part of our homework, was talk about how you can find possible scenarios. And for me, the multiplication principle is the one that made the most sense. Okay? But I'm also going to tie this into another idea today. We've got another definition to consider. Okay? So, and this is going to be a big one because we're going to learn permutations today, and we're going to learn combinations tomorrow, and we're going to find out that they have different definitions. So, let's take a look at permutation and talk about how, number 1, how this is a permutation problem, and number 2, other ways that you can consider this on your calculator. So let's begin with this. What is a permutation? This is an arrangement of objects in which order is important. And that's going to be a large part after tomorrow. I always tell students this. When you learn the 2 opposites, you learn this and this. If you learn them in isolation, it's easy. But when you start to put them together and you've got to decide which one is which, that's where we struggle a little bit more. And that's why I heard from feedback on Friday. When do I use the multiplication principle and when do I use the addition principle? Having all of these things at your fingertips is great, but you got to know when to use what. Okay? So today we're going to be talking about problems in which order is important. Tomorrow we're going to be talking about problems where order is not important. And then on Wednesday we got to differentiate. Okay, when is this a permutation as opposed to when is this a combination? Okay, so this particular example that I gave you right here, order is important because finishing first is not the same as finishing second. Okay, now if these 3 people all got the same medal at the end of the day and it didn't matter who scored first, second, or third as long as you were in the top 3, then the order wouldn't be important. But if there's a distinct difference between first place and second place and third place, now the order is important. Now you get a permutation. Now this is where it can be a little different. In a permutation, you may not be selecting every item along the way. Okay, so I'll go back to talk about this example here. When we did example 2b, we literally were talking about all 8 places. So we had 8 choices, and we had to fill 8 spots with those. Okay? Here, you have 3 choices, and you got 8 different options for those 3 choices. Okay? Back to the beginning problem that I threw up on the board. What if I only had enough room for 2 paintings? Well, it's a little bit different problem than having room for all 4 paintings, isn't it? Okay? So you've got to think about how that's going to impact the problem. Okay? Now, if you don't want to use your calculator, and I don't know why you wouldn't, but if you really chose not to, there is a formula that allows you to be able to figure out how many different ways an object can be taken. And that formula is right up here at the top of the back page of your notes. And I'm going to be honest, I've never used this formula. Because I've always said, if the calculator is going to do it for me, why wouldn't I choose to do the calculator part? Okay? But if you didn't want to, and you just said, I'm going to do all computational work, you're going to do this. Okay? But I'm going to read through this so you kind of understand what we're going to be doing in our calculators. In a permutation, the number of ways that n objects can be taken are at a time. What do we mean by that? The number of ways 8 athletes can be taken 3 at a time. Does that make sense when I say it that way? Okay. How many athletes did we have running the race?
8.
Total of 8. How many places did I care about?
3.
Only the top 3. So I have 8 choices, or 8 athletes, but I'm only going to choose 3 of them. 1 for first, 1 for second, 1 for third. Did I care about 4th, 5th, 6th, 7th, or 8th? No. So I don't need the 5, 4, 3, 2, 1 at the end of this, do I? I only need these choices. Okay? So the number of ways that I can choose n objects and take r at a time is a permutation problem. Okay? Let me show you, before we jump down to these here, how you would do this problem on your calculator. The very first number you're going to put in is how many choices you have to choose from. Okay, back to this example. How many athletes did I have to choose from? I had 8. Okay? Does the order of this problem matter? Yes. And so because of that, it is a permutation. Out of those 8 athletes, how many places are we actually worried about? 3 of them. Okay? Let me show you this on your calculator. You're going to begin by typing in how many choices you have to begin with. How many choices? We said 8. Now, go back to your probability button. There's 2 others, and I told you we were going to use all 3 of these over the next couple of days. There's NPR and there's NCR. We're today choosing NPR because we are choosing a what? Permutation. Tomorrow, we will be choosing a combination. And then on Wednesday, you're going to have to figure out which one is which. We're choosing this one. Hit enter. Now, you can't be done yet. All you've done is told your calculator the value of n in this problem needs to be 8. You still need to give the value of r. Out of those 8 items, or 8 athletes, how many are we choosing from? 3. It equals 336. This is taking your 8 times 7 times 6 for you. Okay? So now, here's the thing. Some people will do this. Mr. Tompkins, I typed it into my calculator and I got 0. How can that be? You can't have 3 items and choose 8 of them, can you? So if you get this, this should tell you that, hey, something's not right here. I can have 8 athletes and I'm choosing 3. I can't have 3 athletes and choose 8. Okay? Alright. Now, let's take a look. I got 3 more examples here. says judges at a marching band competition are awarding prizes for first, second, and third place finishers. If the competition has 5 different marching bands, in how many ways can the prizes be awarded? So does the order matter here? Yes. First place is different than second place, which is different than third. So there's 2 ways to view this. Here's one of them. Using the multiplication principle. I'm choosing 3 teams, right? How many choices do I have for the first team? 5, followed by 4, followed by 3. And if I multiply those all together, we're going to get an answer of 60. Or, because order matters, this is a permutation problem. I'm choosing from a total of 5 teams, and I'm choosing 3 of them. And if I do 5, pick 3, I'm also going to get an answer of 60. Because 5 pick 3 means I'm picking 3 spots from 5 teams. So 5 times 4 times 3 again. So it's kind of like a factorial, except we're not getting, like, if this was 5, choose 5, 5, 4, 3, 2, 1. If it's 5, choose 4, 5, 4, 3, 2. Okay? But now I'm only choosing 3. So, you guys try example 3B. School committee is getting ready to select a president, vice president, and secretary and treasurer by drawing names out of a hat. First name selected will be the president, second name selected will be the vice, third name will be the secretary, and fourth will be the treasurer. If there are 10 students on the committee, in how many different ways can those 4 positions be filled? Alright, so if I want to look at it visually, 4 spots to fill. The first name or first spot's got 10 choices, 9 choices, 8 choices, 7 choices, 9 times 8 times 7 times 6. The order these are picked in is going to matter, because picking you first and picking you third means that you've got different positions within this. So this is also a permutation problem, where you have 10 people to choose from. You're choosing 4 of them. That gives us a total of 5,040 different options for that. Does that make sense for that one? Okay? Real quick, just get used to it. Example 4, A through D. Just type those in, see what you got. Anyone disagree with those? I am going to point out in this problem here, it's the only one. If you have 10 items and you're choosing all 10 of them, but order matters, this is the exact same as 10 factorial. None of the other three up there were going to give you that same answer. If you took 8 factorial, that's not going to be 56. 12 factorial is not this. 5 factorial is not this. But 10 factorial is this. Because the number of items you are choosing and the number of items you are choosing from is the exact same. Alright, finally, told you we're going to bring this all back to probability. The combination for a lot consists of the numbers 3, 4, 6, and 8. You cannot remember the order in which the 4 numbers are entered. What is the probability that you are going to successfully unlock the lock on your first try? What do I need for probability? Number of, I do need total, and I also need the number of favorable outcomes. In this problem here, how many favorable outcomes are there? There's only one. Only one number is going to get you, or one combo is going to get you in there. But how many possibilities are there? That's what we have to figure out. So, you have 4 numbers, but you don't know the order of those 4 numbers. Is order important in this problem? So this is an example of a permutation. Okay? How many numbers do you have to choose from? 4. How many of them are you actually having to choose? 4. 4 pick 4 is 24. This represents total possibilities. How many of those did we say were successful? 1. So our probability should be 1/24. All right, perfect timing. Page 651, 3 through 8, 10 through 30. This is almost all calculator work. Get used to it before we start diving into new stuff tomorrow.